Okay, so in this week's video, I plan on exploring hyperbolic surfaces, spherical surfaces, and planar surfaces, and how the geometries of those surfaces are different to each other. What I plan on doing is using crochet so that I can actually make some of these examples. So I want to make at least 4 different kinds of hyperbolic surfaces, and then I already have a little ball that I made a bit ago, and we can explore spherical surfaces using this, the geometry on those, and then I plan on making a little rectangular sheet of, sheet of fabric so that we can compare and contrast what straight lines look like and triangles, what can happen with triangles. So let's get started. Okay, so let's take a look at what we have so far. So we have this white sheet that's going to represent the plane. We have the ball, which is going to represent negative curvature space. And then I have 3 different examples of positively curved surfaces, hyperbolic space, starting off with the 2x increase every stitch, so the perimeter doubles every time. This one is only 7 layers. If I did the 8th layer, it would actually take just as long as completing this entire thing. It would take an equal amount of stitches to do that. So I decided to stop it here, but you could definitely tell this has a sort of appearance kind of like a sea anemone, or like a piece of coral, or maybe the wrinkles you can see remind you of like a brain. And this is because this sort of surface maximizes the perimeter, the surface area that it offers. And then I have this one, which is increase on every other stitch. So it's a single and then a double. And what this does is you can see that the way that it curves, this is 8 rounds now. You can see it is not as wavy. And then if I go down to the next one down, which is 2 singles and then an increase, this one is almost flat at this scale. But if I continue going around and around, it would eventually become just as wiggly as this one would. So these are the different kinds of surfaces, or rather the more like pure form of the different kinds of surfaces. So you have 0 curvature, flat space. The way that we talk about curvature is you measure it in perpendicular directions. So this may be curved in this direction, but it's actually the product of the curvature in this direction and the curvature in its perpendicular direction. But we could tell that it is flat on this direction, which is why we say that this has 0 curvature, even if it's bent all crazy like this, because it's inherent to the actual surface itself. It cannot change. This sphere has negative curvature, and the way I think about it is the points want to like curve inwards, and then that causes them to eventually come back around and come back together. So they want to spread out, but they're curving inwards, and then they all converge back again on the other side. And then the positively curved space, all the points want to spread out away from each other like that, whereas the other ones want to go and turn back around. And if I go and put up a example of the Poincare disk model, you can see that the way that as we move towards the edge of the surface, it becomes crazier and crazier and crazier. There's more and more space, which is represented by the Poincare disk model up here. Every single one of these, you can tell by the picture that it is, the chunks get smaller and smaller, and that's because that represents this wiggliness. As you move away from the center, it becomes so incredibly dense. So that's the way that we represent it in that model. And in the Poincare disk model, the way that we do straight lines is they are circular arcs that are perpendicular with the disk. On a physical model like this, how do we do straight lines? It is represented by having a crease in the material. So for example, this represents a straight line on the surface. It's kind of hard to see because it's so curved, which is exactly why I made these less curvy models. So we can take a crease, and this crease is actually a straight line along the surface. So I can go and make a triangle by having 3 creases that join together. And then one thing we can see is that lines on these surfaces are very weird. Okay, so I have a crease right here that I made, and I did my best to follow it along with this. So the yellow represents a straight line, and we can see that this, from our perspective, it looks like it curves. If I were to try and flatten this out, it looks like this line curves. So let's see, what does a triangle look like? So I'm going to take this point over here and connect it to somewhere over on this side of the fabric, and then make a straight line back to the original starting point. So let's see what that looks like. Okay, so here is my triangle. You can see it, I have the here, and here are the 3 vertices. So this is the first crease, so here to here. This is the line that I was following as best I could. Let's see, there we go. You can see I tried to follow that line. Then from here to the next one, this one almost, I think it may even go through the centerpiece. So here we go, that's our straight line there. And then lastly, from here to here. These are all straight lines, and it looks like the angles in this triangle are all very, very small. If I go open up all of these angles, you can see the angles that they make are very, very small. It doesn't look like if this were on a normal sheet of paper, it would even make a triangle. With at least a straight triangle, it'd have to be curved, you know? But on the curved surface, straight lines look bent to us. So they look, and this is one of my favorite things that I can actually see now, is on a hyperbolic surface, 2 straight lines, if you try and flatten it out, it looks like they curve away from each other because the space in between them is literally growing. That's what's so fascinating about hyperbolic space. On a triangle, the sum of the 3 angles must be smaller than 180 degrees. And depending upon the curvature that you have, you know, the intrinsic curvature of the surface, highly curved, medium curve, low curvature, the angular excess, the change from 180 degrees is directly related to how big of a triangle you have, which is really interesting. So let's see some of the interesting triangles we can do on a sphere next. So how do we know that what a straight line is on a sphere? Well, you can squish it down and follow where you squished right around and that would make a straight line. Because if you tried to do something like this, well, let's see, if I go and fold it, it wouldn't, if I tried to go, for example, across this line of longitude, we can see we're already moving away from the pole because lines of latitude are not actually straight lines. On the surface, they are inherently curved lines. So if you tried to follow it, you would always be having to constantly turn one direction or the other in order to continue along the line of latitude. So
on a sphere, it's a great circle like the equator. So let me go and draw an interesting triangle on this. Okay, so I started at like the North Pole, made a straight line down, or as straight as I could, a straight line down to the equator, made a 90-degree turn, tried to walk along the equator, then made a 90-degree turn and walked back up to the pole. So this triangle has, I tried to make it 3 90-degree turns, but we can tell that that's definitely more than 90 degrees. So on a negatively curved surface, rather, all triangles, their angles must be larger than 180 degrees. In fact, the largest triangle you could get covers the entire top of the sphere. So it would come down, turn 90 degrees, go all the way around the circumference, except for just leave the tiniest little gap, an infinitesimal gap, and then return back up to the pole. And then that would essentially lock off the entire upper hemisphere of this ball. Therefore, the largest possible triangle would be half of this. And if you made the triangle very, very small, then it would actually, if you were an ant living on the surface, its angular excess, the difference from 180 degrees would be much smaller. And this is historically one of the ways that we measured the curvature of the Earth. We were looking at triangles like on mountaintops, and we would measure the angles across to see how curved the surface would be.
Okay, so I hope this has piqued your interest in curved surfaces, straight lines, these geodesics, and some weird things that can happen if you change the rules a little bit. For the longest time, the only accepted geometries were Euclidean flat geometry and spherical geometry. Back in the times of Euclid, they struggled a lot to figure out why the parallel postulate was so complicated, why it was necessary. This discovery of the hyperbolic geometry, the hyperbolic surface, is why Euclid needed to state that, because if there exists no parallel lines, any great circle will intersect twice or be the same circle and intersect everywhere. If we have exactly one parallel line, then we live on a zero curvature surface. And if we have infinitely many, so more than one, automatically means in this situation infinitely many parallel lines. I didn't demonstrate this on the model, but what are parallel lines? They're just lines that when it's extended indefinitely don't intersect. So that could be, for example, this, if I continued the model, this would never intersect with this line, nor would it intersect with this line. So if I, like, for example, take my yellow geodesic line here, my original short path right here, if I took this, and I could have this as a parallel line that never intersected, so like this path that I didn't draw out, but I could also have intersecting that same path, but not my yellow geodesic over here, could be this one. So what's really interesting is there are infinitely many sets of parallel lines that are distinct from each other. So thank you for watching. I hope this piqued your interest, and I'll see you again next week.